Yeah, no, you are the host. Venkat.
So shall we start?
Yeah, we can start.
Many of people are joined plus. Yes, 8 members have joined. So shall we start now?
Yeah, we can start. We can start.
Okay. Yeah, all right. Good evening, everyone. So from today onwards, we will start the load flow analysis. So far, we have talked about the introduction on the power system analysis. What are the type of power system studies? Especially, we have discussed about the steady state and the transient studies. And in transient studies, we have seen the different classification like electromechanical and electromagnetic studies, and which softwares are being used for those studies. All those details we have covered in the previous sessions. Next, we started with the introduction of ETAP software, in which we have talked on how to create the projects in ETAP, what are the different options that are available in ETAP, and we understood the different ETAP toolbars, and to the extent possible, I have covered all the toolbars in the ETAP. Then we talked on how to create the single line diagrams in the manual method, and how to use the features like auto connect and auto build options. And we have seen the customization of the ETAP libraries. And at last, we discussed on the important feature of the ETAP, that is the multi-dimensional database. Of course, we are not gone in depth of that multidimensional database, like creating the configurations, creating the different presentations and all. But during the load flow, we will cover those details also. And of course, I will try to cover the data blocks also. I have not covered in the previous sessions, and how to create those data blocks and what are the advantages of using the data blocks. All those things I will try to cover during the sessions on the load flow and the short circuit. Right. So from today onwards, we will start the load flow analysis. If we talk about the load flow, the first question that comes into our mind is, what is the load flow, right? Can anyone just unmute yourself and put your answer, like what is the load flow? Any answers? What is the load flow? Any idea?
Sir, load flow means how many value of the voltage and current will be carried at a time.
Okay.
And short circuit current, sir, also.
Of course, short circuit is not a part of the load flow, but
voltage and current will be measured by
yes
at a time. Yeah.
Yeah. Any other answers? Okay, right. First, let me share my screen. Yeah. Is my screen visible?
Yes, sir. Visible.
Yeah.
Yes,
So
sir.
in the load flow, particularly, we are talking about the IEEE 399. Just let me note down all those details. System, okay. Yeah. Talk about the IEEE 399, but this is for the load flow. We'll try to maintain that sheet as well. Load flow. So basically the standard IEEE 399 is what we are going to touch. I am not going to go through the complete 3000 series, because 3939 itself is a depth. So that defines the load flow in a much beautiful way. So if I show this IEEE 399 and go to the load flow definition here, yeah. As per this IEEE 399, given the load power consumption at all buses of known electrical power system configuration, right? Let's highlight this as well. Right. So for the given load power consumption at all buses, which means the load flow will not help you to find out what is the power consumption at the buses. So that is basically as an input to the load flow. Okay. And because many people misunderstands this. Load flow will never ever give, or it will never ever tell what is the load. It will never ever tell what is the generation. These two are the inputs to the load flow, which we have to give it to the load flow. So if you ask me what is the input to the load flow, the input to the load flow are what is the power consumption of at each and every bus, that is as an input. What is the power generation at each and every bus, that is also an input, right? So it just tells like what is the power which is flowing in the branch. That is the reason why we will call load flow is also ideally called as a power flow analysis. Rather than we will call it as a load flow analysis, we can call it as a power flow analysis, because actually if you see, load is not flowing, power is flowing, right? So as many people started using the terminology like load flow, we are also using the same thing, but logically it is a power flow analysis. So when the power consumption at all the buses are given, the power generation at all the buses here, if you power production, power generation at all the buses are given, then this power flow analysis is nothing but identify how this power flow in each and every branch, that is basically called the load flow. So just let it note down here, copy this definition. What is the load flow? So that means we have to give the power consumption at each and every bus. So this is as an input, right? So this is the basically the inputs. Similarly, what is the power generation at each and every bus? That is also as an input, right? And what is the thing that we are getting with the load flow? That is the power flow of the branch. Let me note it down as an output here. So what we are getting is the power flow in the branch. Okay, so when the power consumption at all the buses are given, power generation at all the buses are given, then this power flow analysis will help us to identify how this power flows in each and every branches. That is called the load flow. Okay, so let's read it from the IEEE 399 also, which mentions that for the given load power consumption at all buses, means you need to give the power consumption at all buses. Then a known electrical power system configuration. What does that mean? So here we have to give the power system configuration. Power system configuration. So what does it mean? It means which breaker is open, which isolator is closed, whether the transformer is in service or out of service, capacitor bank is in the service or not, reactor is in the service or not. So they are writing about the power system configuration. So you should know what is the configuration. Also, you have to know which equipments are in the service, which equipments are out of service. That also has to be known. So the third important point is the power production at each generators. As I told already, load flow doesn't give you an output. What is the load and what is the generation? You need to specify what is the load at all buses as an input. You need to specify what is the real power generation at all the buses. That means load also you have to give in all the buses. Generation also you have to give in all the buses. So when the generation and demand is known at each and every bus, then finding out the power flow in each and every branch is basically a power flow analysis. That's what I have told, right? So, as per the IEEE 399, three categories. One is power consumption at all the buses. That is the load at all the buses has to be given. Power production at each bus has to be given for each bus or generator only, because only generator produces the power. So they are telling it's the generator. Okay, for the remaining buses, it is 0. That's clear. And the third one is the known electrical power system configuration. So you should know the configuration, which are all the elements which are in service, which are all the elements which is out of service. That is also as an input. Then it is just finding the power flow in each branches, like rather than writing line transformer of the interconnected network, we can mention it as a branch. Okay. And what are the other output of the load flow? That is the voltage magnitude and the phase angle at each bus. The voltage output, voltage and voltage magnitude, you can say, and the load angle. or we will call it as a phase angle of the bus. Okay. So if the generation at all the generators are known, load power consumption at all the buses are known, network configuration is known, one thing which they have missed out here is the transmission line parameters. So equipment configuration will come under the power system configuration. Okay. So that's why I'm not mentioning it as a separate thing. But in addition to this, the transmission line parameters, they are not mentioned. So it has to be known, correct? Only configuration does not really make any sense. You need to know the equipment parameters like the transformer impedance. You need to know the transmission line impedance, everything. If that is known, then finding out the power flow in each and every branch and finding out the voltage and the angle of each bus is basically the load flow. That is the ideal definition of the load flow if somebody asks. Okay. I hope, is it clear? What is the load flow? Yeah. Any doubts? Okay, fine. Now the next question is, why do we need to perform load flow analysis? Why do we need to perform the load flow analysis? Till now we understood what is the load flow, that has been clearly understood. Now, why do we need to do the load flow analysis? Any answers? Can I expect from the participants? Why do we need the load flow? What is the load flow that we have discussed now? Now, why do we need the load flow? Means what is the advantage of getting the outputs of this, like a power? If you know the power flow in each branch, why you are doing these things?
To understand if the design system is working properly or not.
Okay. Okay.
The selected components is to be overloaded or underloaded, and
Yes.
it is either sufficient to perform the load flow.
Yes. Yes. So here, if you see, so what is the load flow that we have answered? Now let's answer the question, why the load flow? Again, referring the IEEE 399 standard, this states that the load flow is required to determine this following. And we will write exactly the same thing. We will try to add a few more things also as a part of this. So the first component is the component or a circuit loading. Okay. The first one is the component or circuit loading. This might be a little bit confusing. So what is the equivalent terminology which one give it is the, you will call it as an equipment loading, right? This is the simple term. So what is the equipment loading? Let's say I have a transformer of rating, let's suppose it is of 50 MVA. Okay, I'm having a transformer of rated MVA of 50. And now let's suppose the transformer is loaded to 40 MVA, which means the transformer is loaded near about 80%, right? The transformer is loaded at 80%. That means still 10 MVA power capacity is available in the transformer. 10 MVA capacity is available in the transformer. Even in future, in case the generation or the demand increases, this equipment, this transformer will be able to, or it will be capable of supplying that load, right? So that's the essential one outcome of the load flow. Or why do we need to perform the load flow? If you want to find out the power flow in each and every branch in an interconnected power system, then you need to perform the load flow. Let me repeat this. Equipment loading is predominantly the right terminology for an interconnected power system. Okay, so we will mention it as an interconnected power system. Interconnected power system. Okay, so why we are mentioning it as especially as an interconnected system? Because two type of systems are there. I think everyone will be aware of this. One is the radial system and second is the interconnected system. Right. So if it is a radial power system, then you need not really perform load flow analysis to find the equipment loading. What do I mean? If the equipment is connected in the radial system, there is no need to perform the load flow analysis to find the equipment loading. So what is the radial system and what is the interconnector system? Just let me share this thing. One second. Yeah, let me search in the Google for the radial and yes. Oh, right. I think my screen is visible, right?
Yes, sir.
Yeah.
Visible.
So this is simply the radial system, or this we can say it as a simple radial system. So this is the note here. Yes, this is the simple example of the radial system, right? So what is the radial system? This is the typical example of the radial system. Here, each bus is connected to another bus through only one path, right? So what is the radial system? In radial system, each bus will be connected to the other bus through only one path, right? Because if you take the image here, if you take this image here, from this bus to this bus, there is only one path that is available, right? So that's why this we will call it as an radial system. So if there is only one path available between two different buses in the system, then that system is called the radial system. Now, if you ask me question like what are the type of systems that are available, then probably we can answer that in a little bit more with the different systems that are available in our power system. One is the radial system. Second is instead of the interconnected system, I will mention it as a closed rings. Closed rings. How the closed rings will be? The closed rings. Yeah, this is just like some sort of this one, but still let me search. So yes, this we can say it as some sort of this is the radial network, right? This is the radial network, whereas this is a closed ring. So this is the closed ring. So these closed rings have a closed path, but why we are calling it as a closed rings? Because the closed rings have a closed path, but still if anything opens, it will become a radial system. Like suppose if the breaker opens here, so then again it will become a radial network, correct? No? So that's why this is called as a closed rings. So I hope everyone has understand the difference between the radial system and the closed ring system, right? Right? Is it? Yeah.
Yes, sir. Yes, sir.
Yeah.
Yes.
Next one is, let me note it down here. That is the weak mesh system. So what is the weak mesh system? In weak mesh system, we have a very few parallel paths are available. Like suppose, yes, we can say something like this. So this is the weak mesh distribution network. Because why I'm calling it as weak? Because in this network, I'm having a very few parallel paths are available. So that's why we are calling it as a weak mesh system, or we can consider this as a weak mesh network. Suppose if this got broken or if this got broken, okay, so then the network, the interconnections will be, the number of parallel paths is less. So that's why we will call it as a weak mesh system. And the next one is the interconnected power system. Interconnected network in the power system, just like I could not able to find out any images. Yeah, it will be something like this. This is just like our country network. Yeah, you can say like this. Okay, so the fourth one is interconnected power systems. So in power system, basically 4 types are available. One is the radial system. Second is the closed ring, where you if one of the what is the means if anything opens in this closed ring, it will become a radial system. Then is the weak mesh system, which is having a very few parallel paths are available. Then we have a interconnected systems, where you can have a strongly interconnected system, whereas as well as the weakly interconnected systems. Okay. Right. So generally the country networks, everything is come under this interconnected system. But in strongly interconnected systems, you have like multiple parallel paths. Like if you take countries, country networks, so there probably will have some 100, 200, 500 possible paths available between one bus to another bus, right? So that is basically about the classification of this power systems networks. One is the radial, closed rings, weak mesh system, and the interconnected systems. So when we talk about the equipment loading, the equipment loading is not really applicable for the radial system. It is applicable for the remaining 3, and especially it is mostly mostly needed for an interconnected system. Now, having said that, let me ask a question. Why equipment loading for a radial system is not mandatory? Or why the load flow is not mandatory for radial system? Any guess or any answers? Why the load flow is not a mandatory for an means the radial system?
Because the load connected to the single path.
Yes. Yeah. So where is the radial system? I think we could have copied this, no issue. Right. Let me take this example here. Okay. Fine. So here, why the load flow is not required in the radial system? Because power flow is known in the radial system. Let's take this example. Suppose if I am connecting, say, 100 kVA load. Okay, let's suppose I am connecting a 100 kVA load here. The power, how the power flow? Power flows through this branch, correct? Suppose if I am connecting 100 kVA load at this point. Okay, so how the power flow? Power flows from this bus to this point through this path, right? So this is the path. Okay, so that means when the power is flowing through this path, so I will able to find out what is the loading of this transformer and what is the loading of this transformer. Okay, so that means the power flow through this branch is known. Similarly, if the load at the downstream buses is known, suppose if the load at these buses is known. So what, by summing up all these loads, I can easily get what is the power consumption at the upstream, and it is possible everywhere in the radial connected system. So it is a very simple addition itself. And of course, that's the vectorial addition, because the power factor of the 2 different loads will be different. But nominally, natural addition is enough to find out the equipment loading in the radial system. Whereas that is not possible in the interconnected systems. That interconnected systems, I think, let me take a snip of this better.
Sir, another you are open Google page, so mention can electrical distribution system, sir. So kindly you easily show the another system also, sir.
Yeah. Now, if I go to this interconnected network, yes. Yeah. So here what I am explaining is, this is the radial system, right? So in the radial system, it is not there is no requirement of conducting the load flow analysis and all, because we know the power flow at each and every branch. Suppose if I connected a load here, so the power will flow through this branch, and with this I will able to directly get what is the power flowing through this branch, right? So there is no need to perform separate load flow analysis in the radial connected network. Whereas in case of the interconnected system, like having these many number of paths. Yes, like having these many number of paths. So here You cannot directly add the load and you can tell what is the power consumption or what is the power flow through the each and every branch. That is not possible, right? So the simple addition or the manual calculation is very, very difficult. Or you can say it as a impossible. So that is not possible in an interconnected system like this. Okay. But yeah, even of course, in the ring main systems, we can do to certain extent, but especially when we are talking about the interconnected systems, it is not possible to perform the load flow through the manual calculation. Okay, right. I hope this is clear. So in the radial system, if you know the individual loads, then you can sum up and you will get the power flow. So finding the equipment loading is not really a constraint in a radial system, but whereas it is the constraint in the other systems, like the closed rings, weak mesh systems, in the interconnected systems. Okay, I hope this is clear. Yeah. So in radial systems, if you're just summing up the load, you will be able to find out the power flow. But in an interconnected system, you will not be able to find out that. Why you are not able to find it out? Because in an interconnected system, you will be having a multiple paths. If you see here in the interconnected system, you have the multiple parallel paths and each parallel path will have the different impedances. So the power flow has to obey the Kirchhoff current law and Kirchhoff voltage law, everything, right? So you will not be really able to find out what is the power flow in each and every branch unless otherwise you perform the load flow analysis, right? So the very basic, the first purpose of performing a load flow analysis is to find out the equipment loading in different systems like the closed rings, weak mesh, and the interconnected system, but not really needed for the radial systems. But anyway, even if you perform a radial system, load flow analysis for the radial system, you will find the equipment loading, but that is not really needed. Okay. Right. Now, here one more point which you have to understand is equipment loading is just not finding out the equipment loading. It is also give us some information, realistic information about what is the margin available for the future. What is the future margin available? What I mean by that? So when it comes to the equipment loading, let's take one small example of a transmission line. Okay, so the transmission line has multiple ratings. The transmission line, if you take, they have something like a continuous rating. They have a short-term emergency rating, which we will call it as a thermal loading, short-time emergency, and long-time emergency rating, right? And it has a short-time withstand rating also. So what I mean by the continuous rating is nothing but 24/7. This long-term emergency rating may be 12 hours, 8 hours, something like that. The short-term emergency rating may be for 30 minutes. And the short-term withstand rating is like suppose for 1 second every 3 seconds. So it is nothing but a short circuit study. So if you have a different rating for a transmission lines like continuous rating, long-term emergency rating, short-time rating, short-term emergency rating, short-time withstand rating, right? And it is also essentially for you to validate this continuous rating of the transmission line for a normal operating condition. For example, if you are performing continuous analysis, like for the transmission line, okay, let's suppose one equipment will go out of the service, then you may not really compare that with the continuous rating because, for example, if any one of the equipment is out of service, there might be a probability that some elements may get overloaded. So what I mean by that? Yeah, suppose in a very simple way, let's take two transformers. I'm not good in drawing, so please adjust. Right. So let's suppose this is giving to 1 LV bus. And here, let's suppose we have a bus coupler. Very simple system I'm explaining, then we will extrapolate it to the transmission network. Okay, and yes, I think this looks perfect, right? Fine. So let's suppose this is a small network configuration. I think everyone will be aware of this. 2 incomer and 1 bus coupler. Okay. Someone has, can you please mute? Yeah. Fine. Yeah, so this is a very simple network. It is of 2 incomer and 1 bus coupler configuration. Okay, normally here 1 breaker, let's put 1 breaker here and 1 breaker here. Okay, and these are supplying the loads. Let's suppose this is supplying the loads. So in the normal configuration, what is the normal configuration of the contingency? So in the normal configuration, this breaker is closed, this breaker is closed. That means the load on this network will be fed by this transformer, whereas the load on this bus will be fed by this transformer. So individual transformers are feeding the individual buses. Okay. Suppose if there is a problem with the transformer. Okay. Suppose if I want to take the maintenance of the transformer, I means I have to shut down this transformer. So in that case, what I will do, I will open this switch breaker and I will close this bus coupler to feed the loads connected on this bus. So in that case, so this is nothing but the contingency condition. Contingency condition means when one of the equipment is out. So this we will call it as a precisely N-1 contingency. So what is meant by the N-1 contingency? That means one element of the network will get disconnected. So then that will call as a N-1 contingency. So during the N-1 contingency, what will happen? All the loads connected both the buses will be fed by this transformer only. So in that case, the transformer may get overloaded. Okay. In that case, the transformer may get overloaded. Okay. Suppose, let's say if you have a contingency of a transformer failure. Okay. Then probably replacing the transformer with the new transformer will at least take minimum 2 to 3 days. Then what you have to do, you have to compare the transformer with the continuous rating of the equipment. Okay. One is you have to check the continuous rating of the equipment. So when the transformer will be out for 2 to 3 days, then what happened? This transformer shall able to feed the loads continuously 24/7. It has to feed the loads. So in that case, the transformer rating shall be compared with the continuous rating. But say for example, if you have a scheduled maintenance for 2 hours or 3 hours, something like that, then what you will do, you will compare with the long time emergency rating. You will compare with the long time emergency rating, maybe 3 hours or 6 hours. And you might be, if you want to take the shutdown, means if we take up the shutdown for a few checks or something like that, then only probably 2 minutes or 3 minutes, then it is not needed to compare with the continuous rating and the long-term emergency rating. Then you just need to compare with the short-term emergency rating. Short-term emergency rating. So depending upon the contingency condition, emergency rating. Yeah. So depending upon the contingency condition, we have to check whether the transformer will be able to capable of the continuous rating or long-term emergency rating or short-term emergency rating. That you have to compare. Okay. So what I mean by that is in load flow itself, you have a different ratings for different equipments, like the continuous rating, long-term emergency rating, short-term emergency rating. Normal conditions, you need to compare with the continuous rating, During the contingency, you need not really do compare the rating of the equipment of the continuous rating. You may need to just consider the long-term emergency rating or probably the short-term emergency rating. It depends upon the contingency. And in addition to that, this load flow, when we are talking about this load flow will give the details, it gives the information about the available transfer capacity, which we will call it as an ATC. Say, for example, for each and every country, there will be a load forecast, and the loads will keep on increasing, right? Definitely the loads will grow because we are start consuming more and more electrical energy. If we plan the transmission line for today demand, it may not be sufficient for the entire lifetime. Let's suppose if you take the load demand in India, it has grown about like near about 8 to 12% on year basis from 1990 to 2000. Then probably that increase has come down to slightly 10%. Now it is in the range of near about some 8%. That means year on year, the demand is growing by 10%. So if I design the transmission system for today's scenario, then 10 years down the line, that network may not be sufficient. So what I need to do is, I need to probably look at when I'm designing the system, whether the system is capable for the long time, like 10 years, 20 years. That what the assessment that what we are doing, that is called the transmission planning. Basically, that is called the transmission planning. That is called the transmission planning. So probably that is another point which you have to be taken here. Why load flow? It is for the generation planning and the transmission planning. It is for the distribution planning also. Generation planning, transmission planning are already written, and distribution planning. Okay. And again, when we say generation planning, transmission planning, distribution planning, again, this is for the short time, medium time, and the long time, right? So this all comes under the bucket of the load flow itself: generation planning, transmission planning, and distribution planning. And this generation, transmission, and distribution planning has to be planned perfectly with respect to the load flow analysis. And for that, you need to perform another study that is called the load forecasting. Load forecasting. And your success or the accuracy of your results on the generation planning, transmission planning, and the distribution planning depends upon two peoples. One is the brain of the engineer. One is the brain of the engineer who is performing the power system study, which is the load flow. And the second one is the accuracy of the load forecast. Accuracy of the load forecast. If the load forecast is not accurate, then obviously the outcome of the load flow is also not going to be accurate. So when it comes to the generation planning, transmission, and distribution planning, load forecasting is also an essence that is mandatory. And of course, that is not really covered as a part of this wide load flow or as a part of IEEE 399, but still generation planning, transmission planning, and distribution planning are the outcomes of why do we need to perform the load flow. Let's suppose, let's say if you want to decide how much capacity of the generation is needed for, let's suppose 2030, you need to perform the load flow, whether you need 1200 kV transmission line or 765 kV transmission line. How many substations are needed? What about the transmission line? Should we go with a single circuit, double circuit, multiple circuits? How many transmission lines? So to find out all those details, essentially, you need the load flow analysis. Similarly, load flow is required for the distribution, whether to distribute the power to a city at 11 kV level, 22 kV level, or 33 kV level, or 415 volt. How much power, whether it is we should use a conductor or we should use a cable, what will be the length, whether to put the transformer near to the any apartment or probably have a common transformer and probably distribute to the system at 415 volt. So these are all the things which has to be discussed, and all these things can be concluded only from the load flow. Of course, it's not pure technical analysis, it's a techno-commercial analysis, but still the technical analysis of load flow plays a major role on this generation, transmission, and distribution planning. You cannot ignore the load flow analysis for this generation, transmission, and distribution planning, which is not really covered as a part of IEEE 399. Even it is so logical also because IEEE 399 especially talks about the industrial power system. So this IEEE talks about the industrial power system analysis. So that's an industrial power system. Industrial power system assumes like that is for an industry, not for the conventional systems, right? So if you do this analysis for utility, for sure, in addition to that, you need to, in addition to these things, you need to add this generation planning, transmission planning, and the distribution planning. Okay, so if you consider the load flow analysis as per the IEEE 399, which is specifically for the industries, then probably equipment loading and the margin available are the outcomes of the load flow, or why do we need the load flow? Okay, whereas if you apply this, why the load flow is required for the conventional means for the utility scale, then in addition to these equipment loading and the margin availability, you also have to consider the transmission, distribution, and generation planning. Okay. Now, coming back to our topic, what is the available transfer capacity, which I am talking, you need to look at available transfer capacity. So if you see here in the power system transmission network, you may come across the terms like ATC, which is called the available transfer capacity. And you have the CBM, you have the terminology like TRM, and you have the terminologies like TTC. Okay, right. Now just try to understand, because I'm explaining this load flow not only from the industrial perspective, but yes, from the utility perspective also I'm trying to explain. Okay, now what is the available transfer capacity? Suppose let's say the total transfer capacity of the line is, let's suppose 1000 MVA. 1000 MVA is the total transfer capacity, which is the TTC. This is nothing but the total transfer capacity. Total transfer capacity. Okay. Now, what is the CBM? CBM, any idea? What is the CBM?
Sir, total transfer capacity is same as rating of the transformer, na?
Exactly. To the transmission line I'm talking about. So this is the total power that can be evacuated through the transmission line.
Okay.
Yeah. Now, what is the CBM? Any idea? What is the CBM? So this is the called the capacity benefit margin. And TRM, this is nothing but the transmission reliability margin. And of course, in addition to that, you may have one more terminology that we will call it a transmission commitments. Right. Say for example, my total transfer capacity is, let's suppose 1000 MVA. And existing is, let's suppose 600 MVA is the one which is already flowing through the transmission line. Generally, what we will take? We will take the remaining is 1000 minus 600, that is 400 MVA. 400 MVA is the available transfer capacity, but no, because you have to consider some portion of this as a capacity benefit margin and some portion as a transmission reliability margin. Let's suppose I am assuming it as a capacity benefit CBM as 50 and TR means transmission reliability margin as 50. So the total is 1000 minus 600. This is already the existing one, and some capacity benefit margin and transmission reliability margin. So that means 300. Please maximize the screen. I think yes. Yeah. So 300 MVA is the available transfer capacity. So we should not consider 400 MVA. That means total transfer capacity minus the existing one will not give you the available transfer capacity, because you may have to consider two other margins also, that is the capacity benefit margin and the transmission reliability margin. So for this 1000 MVA total transfer capacity, if suppose 600 MVA is the existing one, so the total available transfer capacity will come as 300 MVA instead of 400 MVA. Okay, so this is another important parameter which is needed for the transmission planning. So available transfer capacity plays a critical role as far as the transmission planning is concerned. Okay, so it is clear, like a transmission line has various loadings for different conditions and different configurations, which are studying that power flow has to be compared with the different ratings. Okay.
Sir, but sorry, sir, interrupt you. But
Yeah.
sir, total transport capacity is the 1000. That is, sir. So capacity benefit margin, what is that like? That means, sir, what is the terminology
Yeah.
of the capacity benefit margin and transmission reliability margin, sir? What is the
Okay.
behind the terminology, sir? Please explain.
So wait. So what I understand with your question is, what is the capacity benefit margin, right? Is it correct?
Yes, yes, sir.
So see, if you take a transmission line, okay, if you take any transmission line, so in this transmission line, one is the existing, means one is the total transfer capacity, which I've already explained you, correct?
Yes, sir.
And existing one is around the 600 MVA, which that is also clear. So this capacity benefit margin is nothing but the amount of the reserve capacity that is kept aside just to ensure the reliable power transfer during the emergency conditions.
Okay, sir.
Okay.
But sir, okay, so sir, 400 is the benefit margin, na, sir?
No.
Because
See, this is for the 600 MVA network.
Okay.
1000 is the total transfer capacity. Okay.
Okay,
Out of
sir.
that, 600 is already being used.
Okay,
For the
sir.
600, there may be sometimes it may come, it will go through some emergency conditions, right? So
Yes,
that's
sir.
why some capacity margin has been allotted or and shall be considered for this 600 MVA of the
Yes, sir.
existing system. Okay.
Okay, sir.
So this capacity benefit margin is for the, what to say, for the emergency conditions.
Okay, emergency condition.
Okay. Is it clear?
Yes, sir.
Is it clear?
Yes, understood, sir.
Right. Next, what about the transmission reliability margin? So now here the transmission reliability is to ensure the reliable operation of the transmission network under the different range of conditions. It may consist like one is the emergency condition, suppose to give a little bit of operational flexibility, so to reduce the contingency in the network, so to providing some sort of reliability, some margin will be kept aside for this transmission line, total transfer capacity.
Okay, sir.
Okay, so one is for the emergency condition, second one is to give a little bit operational flexibility and to prevent the congestion in the network.
Okay, sir.
Okay, so that's
Okay,
why
sir.
you cannot simply say this total minus the existing one gives you the available transfer capacity. No, because this CBM and TRM will be added to your existing network.
Okay, sir.
Okay, so considering those two also, you have to calculate the ATC, which is nothing but the available transfer capacity.
Okay, sir.
Yeah, I hope it is clear. Yeah.
Yes, sir.
Suppose if you have if you do any simulations in the software like PSSC.
Okay.
PSSC. So there we will be having different ratings. One is rating A, rating B, and the rating C. So one is with the surge impedance loading of the transmission line. Second is the thermal rating one, and the third one is the short-term emergency rating of the transmission line. Okay.
Okay,
Based
sir.
on the study which you are performing, you can compare the power flow with the different ratings, which may not be really possible as far as ETAP is concerned, because obviously ETAP is not really meant for the utility scale load flow analysis. So when you are performing the load flow study using ETAP, that is probably for the industrial power system network, and it will exactly follow the IEEE 399 standard. But whereas the transmission, generation, and distribution planning, they will not match with the IEEE 399 standard, because that will come under the category of utility. And for that, the simulation software is not ETAP, but for that, the simulation software, what we generally used across the industry is the PSSC software, right?
Okay, sir. Understood.
I guess like the component of the circuit loading is a bit clear with respect to the component loading of the circuit loading. We are talking about the equipment loading. We have talked about the different systems. We have talked about why equipment loading is more important in interconnected systems rather than the radial systems. We have talked about a transmission line has different ratings like continuous short-term emergency rating and long-term emergency and short-term withstand ratings. And in the contingency, either you have to compare with the long-term or short-term emergency rating, or even continuous ratings, depends upon the contingency. We have also talked about what is the available transfer capacity. And from that perspective, we have talked about the generation, transmission, and distribution planning. So load flow is a technical evaluation basically to plan generation, transmission, and distribution planning. And for that, load forecasting is also an important. Load forecast is also an important with respect to the short, medium, and long-term emergency ratings. Similarly, generation, transmission, and distribution planning also short-term and long-term. So essentially, the load flow analysis gives what is the voltage of the substation, what is the transmission line which is needed, what are the other substations which are needed. Everything is given by the load flow, right? So logically, it is just not about the equipment loading. It is about what is the available transfer capacity, what is the transmission planning, what is the distribution planning, and so forth. And like this generation, transmission, distribution planning is not really so visible when we are performing a study in ETAP, because like predominantly we are doing the studies in ETAP for the industries. And probably for the industry, once the industry is fixed, more or less the loads are going to be constant. The load is not really going to grow like the utilities. That's what we clearly say, that the demand on the utility side is keep on increasing. So generation, transmission planning is a continuous activity as far as the utility is concerned, right? I hope this is clear. Any questions?
No, sir.
If you people have any questions, you can put it in the chat, or you can unmute yourself and you can ask me.
Sir, one question, sir.
Yeah.
Suppose if a solar plant is going to connect for a utility through transmission line, then how it's we are doing the simulation ETAP, sir, load flow?
See, as I told you, ETAP is for the industrial power sector network. Like, suppose, let's take, this example here. Okay, let's suppose you have a solar PV, and this solar PV modules will be connected to your IDT, inverter duty transformers. And it will be connected to a pooling switchgear. I can call it as a, this is the pooling switchgear. And from here, I have a power transformers. Let's suppose, let's suppose this is a power transmission network, and here you have your switchgear. And from here, let's suppose two transmission lines are there. And it is connected to, let's suppose, to some interstate transmission system. Let's suppose I'm making it as an ISTS substation. Okay, this is the typical power flow configuration of your solar plants, right? So here, this is the PV module, and here, this is the IDT, inverter duty transformers. And this is your pooling switchgear. Pooling switchgear. And this is your power transformers, and this is your substation. And these are the transmission lines which are connecting it to the ISTS network. Suppose I'm having a 100 megawatt solar plant or wind power plant, whatever it may. It may be either conventional plant also. Okay. So I have a 100 megawatt solar plant, which is connected to this ISTS network through this IDT and the power transformer. Okay. Now, till here, till the substation, yes, you can perform your studies in the ETAP. But once you start connected with the ESTS network, so because see, you can model it as a grid. You don't know you are a complete interconnected network. As far as from the solar plant perspective, you can do the analysis up to the ESTS substation using the ETAP software. But when you are planning, when you are doing the planning, suppose let's say at this substation, let's suppose I consider the substation as some ABC substation. Okay. So when I'm doing the transmission planning, as per my forecast, I assume that let's suppose some 100 megawatt solar plant will be connected at the ABC substation. Right. Now, before connecting this 100 network means whether it is feasible to connect this 100 megawatt at this ABC substation, is it feasible or not? If it is feasible, what will be the available transfer capacity? If it is not feasible, how many transmission lines needs to be constructed? I have to do the analysis for that, right? So for doing such analysis, you cannot do the analysis for a simple network like considering from this ISC substation to another substation. No, you have to do the analysis for the complete network. Means when you are adding some 100 megawatt capacity to that ISTS network, so you can run that load flow with the complete country network, or at least to certain extent to the zone. Zone means within that region. You have to perform the load flow analysis for the region to find out the voltage profiles of the network by adding this 100 megawatt on the system. Whether any of your transmission lines are getting overloaded, and if there is any requirement of the reactive compensation device, any shunt reactors are needed. So to evaluate all those things, it is required to perform the load flow analysis for this network. So to conduct the load flow analysis for the network in ETAP, if you ask me, it's possible, but it is very difficult. It's possible, it is very difficult because PSSC software is having its own advantage. Okay, so when suppose if you take the country of the India network, let's suppose in India we are having some 5,000 buses. So in ETAP, when you try to run the load flow for the 5,000 buses, so your entire network will be displayed. Okay, and it will be a very tedious task to find out the equipment loading or the branch flows in each and every branch. Sometimes it may not converge also. Whereas in the PSSC, the software itself is having some flexibility that you can select the particular zone or select the particular region of the network, and you can perform the load flow analysis, and you can see, means of course in the background, the load flow analysis will be converged for the entire country network. But specifically, if you want to see the specific region, if you want to do the analysis for the specific zone or region, so that can be easily done using the PSSC software. Okay, so that's why precisely if you ask me, this ETAP is for the industrial network, which is having a limited number of buses. Whereas if you take the utility is having some thousands of buses, which will be difficult to run the load flow analysis. And even if you want to analyze the loading of the network for a particular zone or for a particular region, so that will be difficult in the ETAP. But yes, in the ETAP, there is a possibility to conduct the country network, utility network, load flow convergence in the ETAP. That is possible, but still it is difficult to analyze the condition of the network for a particular zone or for a particular region in the ETAP. Yes. Yeah.
Okay,
Any
sir, thank
doubts?
you.
Yeah. Next, any questions? Just let me check the chat. Yes. I hope I think that everything is clear till now.
So one quick question.
Yes.
For the certain utilities ask for a PSSC model as a part of some of the interconnection studies in some of the utilities abroad.
Correct.
So I was just curious that does ETAP have a way of exporting that? If we do all the work in ETAP, can we export the model in a PSSC format for those submissions?
Yes. Let me tell you in this way. as per the GNA regulations, the general network access, that means when you are connecting a solar plant or any RE, not only for the solar and RE, if you take any conventional power plant also. So once you are you have to connect to the grid, first you have to take the connectivity grant from the utility, like that is either the power grid, something it may be, right, to the substation where it is getting connected.
Correct.
So, right. So specifically nowadays in India, not only in India, of course, if you take the European countries and India, most of the utilities are asking the simulations in the PSSC software. So there are two reasons for that. One is already the utilities having their network in the PSSC, right? So if you able to provide this simulation in the PSSC software itself, that will be very easy to adopt them in their existing network. That's the greatest advantage of taking the simulations in the PSSC software. First one. Second one is in the ETAP, you can perform, definitely you can perform the simulations in the ETAP and you can give it to the utility, no doubt in that. But two type of simulations that you generally perform. One is your steady state simulations. Steady state simulations, in which basically you will do with the load flow, short circuit, and reactive power compensation. We call it as a reactive power compensation. Okay, so one is the steady state simulation results that you need to submit, that is the load flow, short circuit, and the reactive power compensation. And the second one is the dynamic simulations. Where basically you will provide the details about your LVRT, HVRT, FRT simulations, ramping control. All these simulation details will be submitted to the utility. Yes, you can provide these details in the in the ETAP network also. You do the simulations and you submit to the utility in the ETAP. But as per the regulations, they asked in the PSSC format. Why? Because if you give the details, like if you give the dynamic details of the inverter, if you give the dynamic data of the PPC controllers and all to the utility in the PSS software, that is easy to adopt and that is easy to verify. So that is the reason specifically they are asking these details in the PSSC. Otherwise, yes, yeah, you can provide this, but specifically because ultimately the details, whatever you are submitting, they have to check in the network, right? The network has been already modeled in the PSSC software.
Correct.
So that's why they are asking in the PSSC.
Yeah, and just are the formats interoperable? Like, can we export in a ETAP model in the PSSC format, or is it completely different? Like it's hard to.
It's completely different.
Got
If you just give me time, 1 second, let me. In this computer, if I have, yes, I can show it to you. It will be something like this. It will be something like this. So this is just like a type of Excel. Of course, it can be possible to see in the single line diagram also. Yes. I hope, wait, let me open it once again. So it will be like this. So here the greatest advantage is ETAP will give you this in this format, right? Whereas in the PSSC, you don't need to create all these things. You can just enter the data in the Excel. Just copy this data and put it in the Excel, and you can just simply add here and you can run the convergence. So no need to create the single line diagrams and all. And as I told you, suppose if I want to, let's suppose If I want to see the network of this only this UrbGen plant, okay, so I can do that. I can do that very easily. Whereas in the PS in this ETAP that is not possible. Suppose the bus number is 206, right? Suppose if I want to see the voltage profile of this particular bus only, this is of course, here we are having the limited number of buses, that's fine. But if you imagine it as a country network, which is having some 5,000 buses, 10,000 buses network, and if I want to see the voltage profile of a one particular bus, here what you have to do, you have to check it. You have to check. You have to find out the bus number, and there you have to check and validate, which will be a very large network. You can imagine with 10,000 network, how the network will look like. But whereas in the PSSC, which is having a flexibility to check, means you can check only the voltage profile of these buses and the loading of the substation if you want to check this. So that can be done easily. So just an example I'm telling you. So the voltage, the bus number is 206 and up to 2 substations. If you want to see here, you can see this. And of course, some rearrangement needs to be done, but yes, you can do this.
Got it, sir. Very helpful. Thank you.
So this is the reason why PSSC is you see here, 206, where is the bus? So this is the 206, right? So here only the network, whatever you require, that only you can display. Whereas in the ETAP, that is not possible. So that is the reason why people are preferring in the utility, especially they are preferring the PSSC.
Right.
Yeah. Yes. Yeah. Any doubts? So shall I continue?
Yes, sir.
Yeah.
Yes.
So you
Right.
can continue.
Sorry.
Yes, sir. Okay, continue.
Yeah, fine. So this is about the equipment loading. Is one of why we need the load flow analysis. Next one is, as per this IEEE 399, one is the component of the circuit loadings, which we have simplified it as an equipment loading. And the next one is the steady state bus voltage. Next one is to find out the steady state bus voltage. To find out the steady state bus voltage. Again, to an extent like finding out the steady state bus voltage for a radial system, you can use the Excel sheets to calculate like voltage drop, which you are going for, which you are generally used for cables, which is a typical example of like finding out the voltage at all buses in the radial system. So to find out the voltage profile or to find out the steady state bus voltage in the radial networks, you can simply use an Excel sheet also, right? And you can use the forward reverse algorithm, which is a simple Excel calculation. Add the current from one side of the network and find out the voltage drop from the other side. Like that, that's a simple. But when you have an interconnected system, as the power flow in each and every branch itself is not known, hence the current in each branch is not really known. So the voltage drop means finding out the voltage drop is difficult, which cannot be known. So finding out the each and every bus voltage is really important, and that is why it is necessary to check whether all the bus voltages in the system are within the allowable tolerance or not. Means within the plus or minus 5%, within the plus or minus 10% or not, that has to be identified. So finding out the steady state bus voltage is really important. And that is what you can see it in the ETAP clearly. Okay. Because in ETAP, you are doing it for a means a very limited number of buses. Of course, that can be evaluated in the PSSC network also. But yes, you can able to, by conducting the load flow analysis, you can able to find out the steady state bus voltage. But there is one interesting fact which is missing here is the bus voltage angle. Bus voltage angle. So the bus voltage logically means, mostly though we call it as a steady state bus voltage, that is the bus voltage magnitude. But there is another term that is called the bus voltage angle also, right? So this is also really important. So because this decides the steady state stability. The bus voltage angle decides the steady state stability. stability, right? So what is the steady state stability? You may come across the terms like the steady state stability and the transient stability. What is the steady state stability is means during the normal condition when the system is connected to the network. So that is the steady state stability. And during the conditions like a transient conditions, like during a fault or during any disturbance happens in the grid. So the ability of the system to remain in synchronism is a transient stability. Okay. Now, what is the steady state stability? Steady state stability means what will be the angle of one bus with respect to other bus is talking about this steady state stability, which means the relative angular difference. You can say it as a relative angular difference. Talks about the steady state stability. If this relative angle goes beyond 90 degrees, then the system will not be stable in steady state itself. Let me repeat my point. If the angle between the sending end bus and the receiving end bus is going beyond 90 degrees in the steady state itself, then we can say that the system is not stable in steady state itself. Because all of us know the power equation, which is P equal to EV by XS into sine delta. Delta, right? When delta becomes more than 90 degrees, the systems becomes unstable. As I mentioned earlier, this IEEE 399 is for an industrial power system. So all the terminology, what they are given is applicable only for the industrial power system. But when you are doing the utility, when you are doing the load flow analysis for generation, transmission, distribution planning, and in addition to these terms, there is something called as the steady state stability. Because 399 talks about only finding out the steady state bus voltage, especially the magnitude, and to the extent we can call it as a bus voltage angle. But the steady state stability, it will not talk about any steady state stability. But whereas once you comes under the purview of the utility, the steady state stability is also one important term which you need to look into. Okay, so the power P equal to EV by XS into sine delta, and this is very important formula. If anyone is not aware, kindly just make a note of this formula. This formula has been derived with an assumption of R equal to 0. R equal to 0. Also, please make a note that this formula is not correct in all the cases because this formula assumes R equal to 0. If you do a manual calculation and if you try to match this with the ETAP, this will not match. It will not match because this formula has been derived with an assumption of R equal to 0. But in reality, R will not be equal to 0. R cannot be 0, right? But still, it gives some interesting information like when the power flow is established between two sources, there should be an angular difference between the sending end and the receiving end. Let's suppose here, this is the sending end and let's suppose this is the receiving end. Okay, let's suppose this is the sending end substation, or here we can give simply we can give it as a like this sending end substation, and this is the receiving end substation. Sending end substation and the receiving end substation. Okay, so when the power flow is established between these two sources, there should be an angle difference between sending end and the receiving end voltage. That means there should be an angular difference between the sending end voltage and the receiving end bus voltage for the power to flow. Otherwise, the power will not flow. Here we can make a statement also like the sine delta. Here, whatever we have discussed, the sine delta, which is basically, you can call it as a delta 1 minus delta 2. Delta 1 minus delta 2. Where delta 1 is the angle of bus, that we will call it as a sending bus. This is the delta 1. And here, this is the delta 2. Delta 2. So, if delta 1 is greater than the delta 2, then power will flow from this bus to this bus. If it is equal, then there will be no power flow. If delta 1 is less than this delta 2, then power will flow in this direction. That means from receiving end to sending end. So if delta 1 is more than delta 2, power flow will be from sending end to receiving end. If delta 1 is less than delta 2 or delta 2 is greater than the delta 1, then the power will flow from receiving end to the sending end. And if delta 1 equal to delta 2, there will not be any power flow. This means real power flow flows always from higher angle to lower angle. Many people misinterpreted this because I have seen many people will claim that power flows from higher voltage to lower voltage. The answer is no. Kindly ensure that with respect to the AC system, real power always flows from higher angle to lower angle, but not from higher voltage to lower voltage. Of course, there is a probability that the real power can flow from lower voltage to higher voltage also, but it can never flow from lower angle to higher angle. Okay, so real power condition for the real power flow is there should be an angular difference between the sending end voltage and the receiving end voltage. And next, it will always flow from higher angle to lower angle. Okay. Yes.
Sir, why? Sir, angle between phase to phase means what? What is the angle where you like to write it that generally cos phi is the angular between the voltage and current, but delta means which what angles?
Yes,
considered?
delta is the voltage angle.
Means
So this
which
is
reference?
V
Sir?
at an angle delta 1. This is the load angle, right?
Mm.
And this is V delta 2.
Okay, sir. Means that like we not calculate
It's not the
delta.
power factor angle. It's not,
Okay.
I'm not talking about the power factor angle because the power factor angle is nothing but the angle between the voltage and the load.
Yes, sir. Yes, sir.
Okay. Here the
Yeah.
delta 1, I'm considering it as let's suppose this is a receiving end substation. Okay. And for
Okay,
this
sir.
network, let's suppose I'm assuming that the delta is 0, right? When the
Okay,
power flow has to happen, so there should be some angular difference from this bus to this bus. Okay.
Okay.
Let's suppose here I'm assuming it as a delta equal to delta. Okay, delta equal to 0 for this bus. Okay.
Okay, sir.
And when the power has to flow from this bus to this bus, then here the delta will be something like some 2 degree. Okay, then the power flow will go. Next, here from here, if there is another bus another line connected to this and it is connected to some substation, let's suppose, and this is one substation, the power has to flow from this substation to substation. Here, it has to maintain some delta angle, load angle. So that is, let's suppose delta equal to some 5 degree.
Okay, sir.
Okay. So this is
Okay.
what I'm talking about. This is delta 1 and this is delta 2.
Okay, sir. Understood.
Okay.
Okay, sir.
Right. So while we're doing the simulations, to prove this with true grips and okay. Let's say when we say the steady state stability, that is also indirectly related to the transmission planning, right? That's what I have told you already. That means if the angle between the sending end bus and the receiving end bus, say for example, 50 degree, angular difference between the sending end to the receiving end is 50 degree. That means the system is almost at the verge of collapse. And typically in India, the angle between the sending end voltage and the receiving end voltage is allowed only up to 23 degree. That means in India, the angular, which we'll call it as a relative angle. You can call it as a relative angle. So the angle between the sending end voltage and the receiving end voltage is allowed only to be 23 degree. Maybe other countries, they are probably going with the 30 degree also. That means in a steady state, the angle separation between the sending end bus and the receiving end bus allowed is only 23 degree, whereas in other countries that is allowed up to 30 degree. Because if it goes beyond 23 degree in India and 30 degree in other countries, essentially there should be an additional transmission line which needs to be added, or somehow this power flow has to be limited, or power flow is a constraint, so that the angle is well brought less than the 23 degree or 30 degree. Now, let's come to the other interesting fact. When this angle separation goes beyond 23 degree or 30 degree, then if you are not able to put into like adding any parallel transmission lines because of the load constraint, or you didn't buy the land from the farmers or something, then it is also probably gives you an idea for the transmission planning with some other elements, like something you will call it as a series compensation device. People heard about this.
Yes, sir.
Series compensation devices. So this is to increase the power flow by reducing the angular difference between the sending end and the receiving end. So what is the series compensation devices? A typical example is like fixed series compensation. Fixed series compensation, which we will call it as a FSC, or you can give it as a thyristor control TCSC, which is nothing but the thyristor control series compensation. That also comes under the transmission planning, whether you have a third transmission line to carry the additional power, or you are trying to use the fixed compensation or fixed series compensation to increase the power capacity, or you want to use thyristor control series compensation to increase the power capacity as well. The power flow, that's all probably comes under the part of the load flow itself. So it is just not about the steady state stability. It is about like to decide whether we need a series compensation or not. So you can write it as a whether we need series compensation is required or not. So this formula P equal to EV by XS sine delta is applicable only when R equal to 0. That means the maximum power flow between the sending end voltage to the receiving end voltage in this formula occurs at sine delta is the maximum value. The maximum value of the sine delta is 1, which is delta is pi by 2 or 90 degree. So as per this P equal to EV by XS sine delta, so when angle between the sending end voltage and the receiving end voltage is 90 degree, then only the maximum power flow occurs. But that's theoretical because the system will not be stable at delta equal to 90 degree. But even despite of that, what we need to really understand is that this condition is with an assumption of R equal to 0. But in reality, the resistance of the transmission line is not 0, but there will be some transmission line resistance. Now let me ask a question, or I just want to answer. When the power occurs at 90 degree, why we are limiting it to 23 degree or 30 degree? Any doubt? Any one can explain? We know as per this equation, the maximum power flow happens from at 90 degree, delta equal to 90 degree. But why we are limiting the angle to 23 degree or 30 degree? Anyone answers, any guess? Why we are limiting to 23 degree even though we have a margin of 90 degree?
Stability issue, sir.
As per this stability is you can go up to 90 degree, right? So if you take some margin, okay, you can limit it 80 degree, but why we are limiting to 23 degree? Okay, right. So here when we talk about 90 degree in the interconnected systems, that means any one of the bus with respect to any other bus of the system goes beyond 90 degree, then there will be an uncontrollable power flow between these two buses. Okay. Suppose, let's take, this is one, or let's take the slip of this. And okay. Okay, right. Now here what we are talking about is 90 degree. That 90 degree in your conducting system is any one of the bus with respect to any other of the bus. It's not between the only the sending end and the receiving end. That 90 degree is the angular difference between any one of the bus to any other bus in the network. Then there will be an uncontrollable power flow between these two buses. But when we are saying 23 degree or 32 degree, it means That is the angle difference between the sending end and the receiving end, which means from one substation to another substation. So steady state stability is 90 degree for interconnected systems. What is the maximum angle of the bus in that particular system versus what is the minimum angle of any bus to any bus in the system? So I hope this is clear. If you have only two bus system, then logically you can go up to 90 degree. But in our systems, we really do not have only two buses. We have infinite number of buses. So 23 in India or 30 in other countries, that is also questionable. Why in India limits to 23 degree, whereas other countries allows 30 degrees? The answer is very simple. See, in India, we are following at 23 degree. Of course, we can go up to 30 degree, but we are limiting our network, means steady state stability limit the angular difference between the two adjacent buses to 23 degree. Okay. But if you are having only two bus system, then the angular separation, you can go up to 90 degree. Okay. So this is what precisely I just want to tell in the steady state stability. So if the angular difference between the two buses goes beyond 90 degree, then there will be an uncontrollable power flow, which means the network will get collapsed. So our objective as a steady state stability, when we claim that, the claim is not between the sending end and the receiving end. The claim is between the highest angle bus versus the lowest angle bus. If your system has only two buses, then literally you can go allow up to 90 degree. That means you have generation at one place and probably you are transmitting on the other side. Only one motor or two motors has been connected. So between the sending end to the receiving end bus, you can allow 90 degree. But unfortunately, our system is not like that. It is something like an interconnected system. So higher angle minus lower angle has to be limited to 90 degree. So whatever the 90 degree here, what I'm talking about, that is the higher angle of any bus to the lower angle of any bus. Okay. And if you suppose, if you have a quite lot of transmission lines in series, let's say you have 10 lines in series, then even if you allow 10 degree in each line, like the sending end bus to the receiving end bus, the total angular difference will become 100 degree, which is beyond 90 degree. But typically our systems are not such radial systems in high voltage and extra high voltage. It is heavily interconnected. So the angle cannot really change something like that as a 10 degree from one substation to another substation. So depend upon the length, depend upon the network. The countries came up with some numbers like 23 degree in India and 30 degree in other countries, depend upon what is the network size of the system. And if the network goes beyond 23 degree, then probably there is a higher probability that one bus with a higher angle with respect to the other bus with lower angle can go beyond 90 degree. So in India, they are not really accepting to go beyond 23 degree in individual transmission lines. So these 23 degree or 30 degree is the constraint of the individual transmission line. 90 degree is the total system, highest angle minus the lowest angle. Suppose if you have a long radial transmission system, then probably this could be much lesser also. So what is the angle which could be allowed has to be decided by the strength of the interconnection, length of the transmission line, and the radial nature of the transmission line. That's what we need to consider. Okay. I hope this is clear.
Yes, sir.
Yeah. Okay, so we will do one thing. We will continue our session tomorrow, means the load flow session tomorrow. So probably tomorrow we will try to finish the load flow, means the purpose of the load flow. And then if the time permits, we will start with the modeling, means we will start with the grid modeling. Okay. Then we will go with the transformer modeling, load modeling, and all, and we will see some one or two practical examples like how to do the load flow, how to perform different configurations, how to create configurations in the presentation views, which I have missed out in the ETAP session. So that I will try to cover in the load flow sessions. Okay. Yeah. Any doubts? Any doubts in this till now?
Sir, I have one confusion.
Yes.
You said that for two bus we can take 90 degree difference between two angles.
Yes.
Again, you said for the whole system it is allowed.
No. Wait, ma'am. here what I'm telling is that 90 degree, what I'm telling is that is from the suppose, yes, this is the interconnected system. And here, let's suppose this is the bus number, let's suppose 1, for example, this
Your
bus.
screen is not visible, sir. Sorry.
Okay, 1 second. Okay, right. Suppose this is the bus number 1. Okay, let's suppose this is a substation. This is bus number 1. This is bus number 1. Okay, and let's suppose this is bus number 2. Let's suppose this is having bus number some 50, or here it is some 70, something like that. Okay, so here what I'm talking is the difference between the bus 1 and bus 2. So these two are interconnected, right, to a direct transmission line. Here the maximum allowed limit is 23 degree or 30 degree. Okay, the 90 degree what I am talking is about, let's suppose this is at some 1 degree, for example. Okay, and let's suppose this is this bus 70 angular is, let's suppose, something like 85 degree. Now from this bus to this bus in the interconnected system, the angular difference is almost near about to 90. If it crosses 90, then there will be uncontrollable power flow from this bus to this bus. Okay, suppose if you are having only 2 bus system, means if your system is having only 2 number of buses, then you can go up to 90 degree. Suppose if you have a radial system, you have a generation here, and you have a load connected here. Okay, if your system is only like this, then you can go the angular difference up to 90 degree between these 2 buses. But unfortunately, our system is not like this. Our system is an interconnected system. So the 90 degree what we are talking about in the interconnected system is the lower angle of any bus to the higher angle of any bus. Okay. Whereas if you see the angular difference between the 2 adjacent substations which are connected by transmission lines, there the angular difference allowed is maximum up to 23 degree. So this is precisely what I want to explain. I hope this makes the sense.
Yes, sir. Thank you.
Yeah. Yeah, any questions?
Sir, any reference of this angular difference to be used for the utility?
Yeah, you can refer the transmission planning criteria by CEA. There is a document called transmission planning criteria, which has been updated in 2023. So you can refer the document that is available in your CEA website.
Okay, sir.
Yeah.
CEA.
Yeah. Central Electricity Authority.
So do we have that one? Can you share that one?
I will try to share.
If not document, at least snap of this.
No. That's a public available document. It's not a confidential and all. It's a public document. So I will try to share.
Fine, sir. Thank you.
Yeah. Yeah. Any more questions? Yes. Yeah. If it is clear, then we will end the session today. And tomorrow we will continue our session on the load flow analysis. And if the time permits, we will start the modeling of the grid also. Yeah. Thank you. Thank you, everyone. Thank you. Bye.
Thank you.
Thank you. Bye.